Right, so welcome back to implementing a dependently typed language starting with simple types. So let's go through the code step by step and look at the specification and what it means in terms of the implementation. So first thing you'll notice is that we separate the inferable and the checkable terms. So one's I term for inferable and C term for checkable. So we have the annotated term on the top and takes an input, term and type. And then we're using De Bruijn indices for this. De Bruijn indices is used for the local representation, and then we have some global names. So free name, that's like name as a string here. So a little bit of both. And then we have the application, which is something on the left, which is the inferable term, which we're hoping we're going to get a function type. And to the right, we have a checkable term, this thing essentially, which checking application. Oh, inferring it. And then the checkable one is we can put the inferable term within it. You remember that conversion from one to another. Where is it? Yeah, that's for the check. And we have the lambda. So for the lambda, we just get some checkable term to check that it's lambda.
What does the colon
sorry, yeah?
in the iter, the last.
Oh yes, this is just we're using this to mean application, just kind of making it explicit what's happening. So rather than having app C term, we made it in the middle so that it's kind of a bit more natural as a syntax. And then here we have values, and we're using higher order abstract syntax for the value.
Excuse me.
Yeah.
Make it larger.
Larger.
Escape X and then type zoom in.
Zoom? No, zoom is not nothing.
Maybe just Control plus.
Okay, control. Yeah, right. No.
I think it's just like Control X and then plus.
Control X plus. Oh yeah, Control X plus. Okay, cool. Oh sweet. Yeah. Is that good enough or?
It's very
Okay. Sweet. So. Higher order abstract syntax, which means that we're using the inbuilt function type of Haskell to represent our function type. It has advantages, meaning that we don't need to worry about how we implement substitution, which is good, but unfortunately it means that we you can't show a function type. So we need there's a special function somewhere for quoting, which will, I will say it later, it will translate this term into a showable representation. And we have the neutral values here, which is kind of like, if you remember the syntax, it's pretty much exactly what the syntax for the neutral values is. You can see it here, and you can see it here. Pretty much the same thing. Then we have the kinds for type checking that our types are well formed. And we have this thing info. It's used for the context. So essentially, we have the name of an identifier and its information. And the information is either its kind or its type, depending on whether we're dealing with a type or a term. And our environment is just a bunch of values, a list of values. And here we have a few helper functions for one's for generating the value of the free variable. And for applying, so for if you take a higher order representation, we can use just regular application to kind of perform computation there. So next thing we're going to look at is the evaluator. So extremely simple, and I mean, essentially we have two functions. One evaluates the inferable, and one evaluates the checkable term. And you can see that there are some cases where they're mutually defined. Inferable calls check sometimes. So again, if you look at the evaluation rules, well, sorry, yeah, wait. So okay, does this is this make sense to anyone, or is anything you want me to clarify there? So, for example, we have free and bound variables where the bound variable it has the De Bruijn index. So we're just looking up the name and value corresponding to whatever the De Bruijn number is. And then for the global representation, we're also doing a lookup, but now we're looking for text value. And then application goes back to the vup function I just showed you, which recursively evaluates the two sides of the function abstraction, and then performs the application on them. And then, yeah, this is how you go from checkable, and then you infer it. And then, again, if you're checking the, evaluating the lambda term, then, again, you have to kind of recursively evaluate the function bodies, and then you wrap it back into lambdas. So let's have a look. Then the interesting bit is the type checker function. So the first one is, I guess, we're checking that our function type is well formed. So we're just checking the kind. And we have the two cases where we have the free variable, and we're just looking it up in the context, and we're checking that the annotation we're looking up has kind star. And if it does, then we return unit. So okay, so this is the result monad, actually. So the result monad is essentially we're just using for error tracking. So yeah, in here we have for the check we're returning a unit, and for the inference we're parameterizing it by the type because we want to return the type and use it for something else. And then yeah, if we're checking the kind of a function type, then we just recursively check that each of its sides evaluates to a type star. Does that make sense?
Does anything ever not evaluate to a type star?
Yeah, we only have, well, if it's going to stay as a lambda, if it's going to stay as a lambda application, then it can evaluate to star star, but then stop there. But yeah, so either star or some combination of star to star. It's very simple.
Star is also in category of star.
Yeah, yeah,
So,
yeah.
in this, actually, in all these type systems on the lambda queue, you only have terms or something of in category or in space of stars, right?
Yeah, yeah.
So beyond the lambda queue to have other kinds than term or star, right?
Yes, yeah. So
yeah, so to answer this question, there would be no point in having something beyond star.
yeah, and we're also we're going to have an explicit axiom of star is type star. So we're not going to have a we're going to have a bit of an inconsistent system there because it's a little bit easier to implement for the first time. Well, once we get to dependent types, essentially, I guess we'll get to that later. But yeah, as the first exercise, we're doing a simpler one, and then if you want to have universes, then a little bit trickier. Right, so then we have the inference of type, and again, it needs to take, so this is we need, so it returns the result monad with the type, and it takes a context and an inferable term and a De Bruijn index. And the I-type 0 is like the base case where the De Bruijn index is the 0th index. And let's see what we're doing here. So the inferable types are the cases are the annotation expression with some type, and then we're checking that the annotation actually values the star, so it's a type, and then we're checking the type of this De Bruijn index which we're passing, and within the context, and using the expression and the type which we got from here. And then we return type, assuming that we succeeded in the check. So again, you can see how this comes from the rule for checking notations. If I maximize this a bit, to infer the type of annotation, which is the thing on the bottom, then we need to do the check, and so we're calling the check kind and check type here. Then for the free variables, we're just going to look up that the thing has the type. We're just doing the var rule. Very simple. And the final one is the application. So again, first we start by inferring the type of the at the index II, and then we case match. So and then you know how you guys had the questions with this earlier. So essentially we've got this case match where if it's not a function type, then we get an error, and if it is a function type, then we put this into the check. So we put this into the second part. Does that code make sense? So essentially it kind of describes this in the monadic style, and you can see it sequentially.
Just a question. Is everybody here familiar with De Bruijn indices? Because it's been new to me when I learned about them.
Yeah.
A question to the audience.
Oh, wait, a question, yes. Raise your hand if you're familiar with De Bruijn indexes, please. Okay. So a few people aren't. Essentially, yeah, you're just representing your okay, so the Bruijn indexes, they aim to solve the problem of being able to refer to the variables within it's a good way to describe. Would anyone else want to help out and define De Bruijn indexes kind of concisely?
So I won't be able to help defining them.
Yeah.
I will describe how I understand their usefulness.
Yeah.
When you have a program and it has identifiers declared, be able to shadow identifiers of the outer scopes by the ones in the inner scopes. You don't want to be messing with strings in the AST and assigning them to values via a map string to a value. Rather, what you want is you want to assign each identifier an index in the AST, which is the rules of deriving the index are, I guess, simple. I just don't remember them. This gives you a shadowing from upper scopes for free.
Yeah.
That's why our environment of values is just
There's
a
one
list.
important function of them also, apart from that, I guess, if I remember correctly, it's because you need to rename variables in the process code for renaming. And you don't want to actually keep track of these renamings because that's messy, but you want to know where the variable finally is bound to. Right? And the Bruin index gives you that information because it gives you an index of variable in a lexical scope around it, so to say. So you don't have to remember all these alpha renamings that can happen in process of beta reduction. Was that correct?
Yeah. So
Basically it's referring to a source, so to say, of a name, instead of remembering all the chains of renames that got in there.
This allows me to substitute without changing
The actual name, alpha 1, alpha 2, or something like that. You just know that this variable is bound here, this one is bound here, and you can process that. I guess that's the most important function of the Bruin indexes.
no, you're on the right track. And just to mention alternative ways of doing it. There's also in Haskell there's a library called I think it's called Bounded. Unbound, yes, that was it. So that kind of takes care of all the nominal stuff for you. Is a nice abstraction of it. Is that based on nominal logic? Do you know? Or something similar. So essentially kind of abstracts away from all of that. So it was an alternative representation I was thinking of because the Bruin indexes can, they're the classic way of doing it, hence why we're going with them here. But they can be a bit of a pain to work with. So yeah, that's one alternative I can suggest. Let's see. Right, yeah, so then we've got our, where did we left off? We've done the inference, and then, the checking function, again, takes the index and the context, the checkable term, the type against which checking, and the result. So again, we had check kind earlier, and now we have check type. Here's our two cases where we're looking at it, the check rule and the lambda rule. Again, I think fairly simple nutty code. Self-explanatory, I guess, and then, so in here we also use substitution. So here we have an implementation of substitution. And again, so we have at index I, and we have an expression, and then we have what were the term for substitution, and then we get as an output a term. So again, just recursively substitute annotations for bound variables. Check that our index corresponds to. So we're looking at where the index we're given corresponds to the index we're looking at, or leave it the same. And for, I guess, the interesting case for the application, we're just recursively going to substitute its insights. And then again, for the checkable terms, the same thing. I guess, yeah, any questions there? As you can see, so once you have the bidirectional type inference, the nice thing about it is that literally there's no real mystery about how you're translating. Everything on the right is, almost word to word, just different syntax things we have on the left. Is that visible to you guys, or any? Is there any link you don't see there, like you want me to clarify?
Sorry, the link between what?
Okay, so there's a link between stuff on the left and the stuff on the right. So kind of the idea is that.
In general, yeah. In general, yes. It's just that I haven't seen slides for substitution, so that's why I'm stuck on your question.
Oh yes, yeah. I guess.
But we can omit them.
Yeah, the substitution was implicit. Right. So then the question is, what else can we look at? This is like the main meat of it, like the stuff you want to be concerned with when you're developing your type system. Then, of course, as any language you're building, from a practical standpoint, there's going to be a bunch of glue code putting everything together. So, for example, here we have this big interpreter type, which takes parameterized by the particular syntaxes we're using, and the type checking, the pretty printing functions, the parser. So we can have a look at that briefly as well. Let's see, parser, using standard monadic combinators. Let's see, is there anything particular? There's a few reserved words. So let's see, type parsing, parsing terms. Is everyone familiar with monadic combinators? I'm afraid it's, yeah. It's the bit of background knowledge which is assumed, because it would be a whole different lecture to explain parsing combinators otherwise. And then, what's the pretty printing library? A printer. So here we're using the John Hughes pretty printing library, and again, fairly self-explanatory. Right. Let's see. Okay, so we can try and run this and see if we can do anything interesting. This is a very simple type system. Is this visible? My second window. CD. Oh crap! Where did I put this? Oops. Okay. Okay. So here is our little REPL for this. So damn it. I think this is the higher my terminal goes for some reason. Shit. Okay. What's anyone has a solution idea for this? No. Control minus works, weirdly. Yeah. Wait. Control. Yeah, I think so. Yeah. Damn it. eShell? Oh, how would you use that? I'm afraid I'm not familiar with that. Oh, cool, nice. So.
It's a little bit wonky with like up and down and like so.
Yeah. Wait, shit. Where are we? Sources, slim deploy. Test build LP. Okay, is this better. What was the Control plus, Control Shift plus?
No, but I think that's fine.
Oh, okay, cool. Right. So let's have a look. What was the? So we can load the prelude. Oops, prelude. Oh. I should load prelude st simple types. So there's a few things implemented here using the church encoding, which is who is familiar with church encoding? Okay. Yeah, cool. Yeah, most people here. So essentially, we don't have. So we have our very simple type system, and there's not really a way to define data types. So instead, what we could do is we could use can use church encoding. Oh wait, I'm giving you the wrong. Should be a Steam. So you had a brief glimpse of the advanced one, advanced language. Just a moment. Let me try. Okay, here we go. Should be st. Right. Okay, that makes sense. St. Shit. Here we go. Here we go. So load. Prelude st. Okay, wait. Okay, load. More? Okay, right. Oh yeah, shit, I see it. Prelude st. Ta-da! Okay, here we go. Here we have some things, and let's see. So let's go for type. Well, I guess you see all the types. I'll show you the actual code for it as well, just to see how that works in the prelude.
Is it actually correct types? Because it looks like some brackets are missing.
Yeah, it's removes them because removes them for evaluation. Let's see. So here we have a few examples of. Here we have a definition for the naturals, which is assume there is some constant n of kind star, and then assume assume that 0 has type n, and then assume that some constant s has the type n to n, and then you can do so these are the church numerals, which are this encoding of naturals you do when you don't have the data type definitions. So you can kind of do stuff with them. But admittedly, because essentially this is, originally when non-calculus was invented, it was meant to be a meta language for doing mathematics. And so the idea was that you could do everything just using the function type. And so in this view of the world, everything is a function, whether 0 or 1 or 2. And so you have these really weird terms, but uniformly they become these types. And if you put this into the REPL and you try and perform addition on 0 and 1 or 2, then we can check that it's actually going to give you the right term. But yeah, it's a little bit messy.
It seems that you must put type signatures for each lambda in this type system.
Mm-hmm.
Yeah, because if you don't put it, wouldn't infer any
Yeah.
type for lambdas.
Mm-hmm. Yeah, so, okay, it's not the most exciting type system, admittedly. And so the the next step would be to look at a generalization of that into dependent types. So, so let's have a look. Number 2. Okay, so this is where the fun begins. So far, we just had the background for it, and now we can get to it. So, okay, first is the abstract syntax, and the question is, what do you think changes at this stage? So what we're gonna do here is we're gonna keep as much as possible from all the rules you've seen. And then, yeah, so anyone have any idea what's gonna be the new abstract syntax? What's the small change from the previous one?
You're going to have functions from types to terms and vice versa, maybe?
You're on the right track. We're gonna have a new constructor. Yeah, I suppose, yeah, well, yeah, we're gonna have the dependent function type constructor, which is, here we go, the dependent function space. So for all x p to p dash or rho is the Latin name for it. But the second big change here is that you'll notice that in the first slide we've had separate syntaxes for types and for terms. Here we only have one syntax tree. So this is the big difference between dependent types and all the other aspects of the lambda cube, because when you have dependent types, you collapse the distinction between terms and types. They all live on the same level. And so, yeah. And here we have also, in addition to the dependent function space, we're also adding star, which is the type of types. You can call it informally a kind, but we don't technically have kinds in this world. But yeah, this is going to give us the, is anyone who's familiar with the whole consistency and paradoxes issues of type theory? Okay, so.
Are you assuming Girard paradox?
Yes, so you could, yeah, you would have it draw, you can find, you're not assuming it, but you're able to derive it here. You're not like saying, yeah, we're going to have the paradox here, but is a consequence. So essentially, this also, I say we'll get to the second, but first we'll just go through the evaluation rules. So very, very minor change from the two systems. We still have all the existing rules, and we've added the evaluation for the the correspondence to this one. So star evaluates star, type in type. And here we have the evaluation of the dependent function space. And that can be a little bit tricky to articulate. So I'm going to do my best, and if you have questions, then definitely ask.
Regarding star evaluates star, is this the same star? So types can't change? Or?
Oh, I see. No, you do have types can definitely evaluate. So this is more like, you can think of it as a normal form, kind of how we have x evaluates to x. You can also see it as if you just have a star, it just stays a star. Because this thing, the evaluation here can also be a type. So the for all x of type row to row dash, you can use it to define types. So okay, let's see. Let's try and read this. So we want to evaluate the thing on the bottom left to its normal form somehow. So what does that mean? It means that the thing on the left, p, evaluates to t, and p dash evaluates to t dash. So you evaluate the function application part, and you evaluate the body. So yeah, I guess fairly. Does that make sense? Yep.
Can you maybe first explain, so that for all x, colon, p,
Yes, yeah.
how are there parentheses around the x, colon, p, or around the p, dot p, or how
You can see, you can imagine, let me see if I made any special notes for this. You can imagine the dot as the, instead of the arrow. So because we already used the arrow symbol, so we don't want to confuse the terminology, so we're using dot in this case. But essentially, it means that there is, x is some kind of value, which could be a term of some type, or could be a type of type star. And then this value can occur in the range of the function. So x can occur in p row. So essentially this means that we take in the this value, and then we take our take in p, and then as output we get p dash. Let me see some nice example for this.
So this is like a lambda.
Yes, yeah. It's dependent lambda essentially. Yes. Oh, yeah. Let me draw an example. So. Oops, shoot. Okay. So the classic example would be the identity function, the polymorphic identity function. So we have ID of type x has type, and then we take the second argument, which is y of type x, and we return an x. Sorry, don't block it. Okay. Essentially, for in Haskell, because this is implicit. So in Haskell, you just have a to a. But if you were to make this explicit and using instead of polymorphism using dependent types, then you would do it this way. So you take in a lambda x, which is a type, and you take in a lambda y, which is a value, and you return that value. And if you have ID, you need to apply it first to something like, I don't know, nat, and then you apply it to a particular natural, and that evaluates to the natural.
Okay, so the second line you wrote here, to make it more explicit, you could add like a type annotation on the first axis of type star, and then the y is of type x.
Yes, yeah, that's very correct, yeah. I kind of defaulted to the more Haskell syntax, but yes, in our case it would be x of type star. And I guess, okay, so another one would be the constant. And in this case, we're taking 2 parameters. So, we're taking x type star, and we're taking y of type star, and then we're taking a of type x, and then b of type y, and returning a.
So A or X, how do we write it?
Okay, yes.
X.
Oh, of course. Good catch.
So how does it correspond to this for all notation, for all and dot notation?
Right. So for all, you can just imagine it as a lambda from x to p dash, and this is the p dash is like an expression.
From X to row to row dash?
Okay, so this would be ID of type for all x of type. It would be let's see, p to p. P would be the expression, and then p row would be the output, I think. Yeah. So for all x of type, we get that, wait, no, this is dot. Y of type x evaluates to x. Sorry.
So the dot is after type.
Yeah, because this is the input, and so yeah, x of type. So yeah, for all x of type row, we have an expression row dash. So
X of type row is in brackets.
yeah, yes, x of type row, and then we have the dot or the single dot. For all x of type dot, we have the expression y of type x evaluates to x. Mm-hmm.
Now I'm a bit confused what the dot means.
Okay, the dot, you can view it as the dependent function arrow. So think of it, we have two arrows. We have the regular arrow and the dependent function arrow. It's just kind of, so you can separate it to notations. So yeah, good question. I always have notation questions, definitely. They're good. So yeah, that's just that we have this one thing, and then dependent arrow, and the second thing. And the important thing is that this x can occur within this expression, so within it, somewhere.
How this is different from normal polymorphic function?
Yeah. Okay. Yeah. Good question. So this, you know how I mentioned how dependent types can be can implement all the other type systems. So technically, yeah, this is how we subsume polymorphism. You just say for all x of type. It means exactly the same thing as regular polymorphism, but the difference is that you can do other things. Is that you can say vector is for all n of type natural, and then you have the dot. Well, I guess I'm using a bit of a Haskell syntax here because we haven't defined lists or anything, but you'd essentially have you take in a nut, and then secondly you take another argument. Well, let's make this simpler and not do vectors. Let's do finite lists. So fin would be for all finite numbers. So fin fin is a type which takes in a natural and returns a bounded type. So essentially, you're saying what's the maximum value the term of this type could take. So it takes an n of type nut, and oh, thank you. And what do we return? Yeah.
This x type is just the regular type.
Mm-hmm.
Now in value.
Yeah.
It's normal polymorphic.
Yes. Yeah. Exactly. And yeah. Let's see. I guess yeah. We'll get to the finite number later once we start implementing actual things for it. Let's see. Okay, next thing is going to be the type checking rules, and I guess maybe let's do that after the break.